Hello and welcome to a flipped classroom lecture on the equations of motion for acceleration. If you haven't done so already, you can download and print out a hard copy of this presentation, and then you can use that to help you follow along, but that's totally optional. It's up to you. So I'm going to introduce four equations of motion for acceleration. But before we even do that, the big question is, should you even use these things? Because we already have an equation for constant velocity. So how do you choose what to do? Well, you have to read the problem carefully. You have to determine if the motion question is constant velocity or if there's acceleration involved. If it's constant velocity, don't use any of these equations we're going to talk about, just use the constant velocity equation. If it involves acceleration, then this lecture is for you. You're going to use some of those equations instead. And you have to decide every time you read a question about what to do. All right, I'm going to hit you with four equations of motion today. So before I do that, I want to talk about what all the symbols in the equations mean. VF means final velocity. The V stands for velocity, and the V is for final. That's the velocity at the end of the motion. VI is initial velocity. The V is for velocity. The I stands for initial. X is position, same as it was in our velocity equation. A is acceleration, and T is time. Some values are going to be positive or negative, just like they were for velocity. And just as we talked about in the velocity equation, a positive value means that it's pointing in a certain direction, and a negative value means it's pointing in the opposite direction. Okay. So here are our equations of motion. I'm going to create another video, talk about where these came from. So please watch that. For now, though, put that question aside and trust me, at least for the next few minutes, that these equations are correct. Our first equation of motion relates final velocity to initial velocity, telling us the final velocity equals the initial velocity plus acceleration times time. The next equation tells us that distance equals the average velocity times time, which makes sense. It looks just kind of like the velocity equation, except I put a little average velocity. And to take an average, you take the initial velocity and the final velocity and divide them by 2. That's how you take an average of two numbers. So that's where this part comes from. Now our next two equations are a little more complicated. The position, or rather change in position, equals initial velocity times time plus 1/2 at squared. And then our last equation, final velocity squared equals initial velocity squared plus 2 times acceleration times distance. Whew! Now, why am I giving you 4 equations? Is it because I want to torture you by making things more complicated? Actually, no. It's because if you encounter a problem, you can pick one equation, and if you pick the right one, you can solve pretty much any problem in motion in one single step. You grab the equation, you plug in numbers, you solve for what you want, you're done. It's great. So that's why I'm giving you 4 equations. If I only gave you 2 of them, then some of those would be multiple steps. You're welcome. So let's do a problem with these equations of motion, and then we'll talk about some strategies. So sample problem number 1, a car is moving at 15 meters per second, and it speeds up to 25 meters per second in 5 seconds. How far distance did it travel? So these numbers are actually fairly realistic for a car. 15 meters per second is about 30 miles an hour. 25 meters per second is 50 miles an hour. So it's entirely possible to do this in a regular automobile. Okay, so let's tackle this problem. How far did it travel? First thing I'll do is draw a diagram. So I've drew one right up here. It doesn't have to be fancy. you've got a car going at 15 meters per second. After some distance, it's now moving at 25 meters per second. We'd like to figure out what that distance actually is. So I write down what I want. I want to find x, the distance. I write down what I know. The initial velocity is 15, final velocity is 25, and the time is 5 seconds. Now I consult my list of equations right here, and I need to pick one that's going to work for me. Now, first of all, I better pick one that has what I want. I want x, so I should not pick the first equation because the first equation doesn't even have what I'm looking for in it. So forget that one. Now the next three equations have x in them. This is x equals something, and even the third equation has x. If we choose that one, we'd have to do a little bit of algebra to solve for it. Okay, so we got to narrow it down further. I know initial velocity, final velocity, and time. So I have to pick an equation where it has x, and it has only these three variables. Now, a nice easy way to do this is to think about what we don't know. We don't know acceleration. We don't know what a is. So we don't want to pick an equation that asks us for that embarrassing question about what a is. And you can see a right here in the third equation, a in the fourth equation. Oh, I don't know what a is, so that would be kind of inconvenient. But the second equation has everything that we know and the one thing that we don't know. So we can use that and solve in one single step. So let's do it. So I've still got what I want, what I know. I then write down the equation that I'm going to use. Just write it down. Don't plug any numbers in it yet. Then I plug in the numbers. VI is 15, VF is 25, time is 5 seconds. Then I do a little bit of math and I figure out my distance, which happens to be 100 meters. Easy as pie. Now, what I did to do this, I'll break it down to a couple steps. First, I drew a diagram. Then I wrote down what I wanted and what I knew. I picked an equation and just wrote that equation down. And then I plugged in the numbers into the equation. I wrote that down too. And then my last step is I just did the math and solved for my variable. I want you to do this when you do problems. I'm going to insist that you follow these steps on the test. I'll literally write them up on the board, and we'll take points off if you don't follow them, because they are so amazingly helpful. I follow these steps when I do these problems too. All right, let's do one more sample problem and then be done. Here you go. Consider a car moving at 27 meters per second. If the driver slams on the brakes, the car can decelerate at a rate of 9 meters per second squared. What is the stopping distance of the car at this speed? So, go ahead and pause the video and try to solve this problem. I'll wait. Okay, let's do it. So I drew a diagram. Initially the car is moving at 27 meters per second, and then it comes to a stop, which means its final velocity is 0. Oh, I didn't give you that number in there, but stopping distance, you have to know it comes to a stop, which is 0. We'd like to figure out this distance. So I want the distance. I know initial velocity, final velocity, and acceleration. And I wrote acceleration as negative 9 meters per second because the car is moving that way, and the acceleration is going in the opposite direction because you're slowing down. So that means the acceleration is negative. Okay, now I pick an equation, and the fourth equation will work wonderfully for us. It has x in it, and it also has everything else that we know, and doesn't ask the embarrassing question about what the time is, because we don't know that. So I write the equation down. I plug in numbers here. VF is 0, VI is 27, and then we have acceleration is negative 9. And then I do some algebra 1, and I solve for x, and I get 40.5 meters. And that's all there is to it. So good luck.